through it. Okay, so is everybody with me so far? Pretty simple. We just took the GCD of 8 with 18. We got 2. We wrote 2 in terms of 8 and 18, and then we scaled it up to negative 6. Negative 6, of course, it would be a great thing to do, would be to just write that as 5 minus 11. Because those are the numbers that we're working with here, right? So 5 minus 11 is going to be 18 times negative 3 plus 8 times 6. Okay?
Okay, you use negative 6 because that was the difference of 5 and 11?
Yeah, this is negative 6 here. So I had a 2 here, so I multiplied by negative 3.
So we could have done positive 3 as well.
You could have, I just took, well, if you did positive 3, you'd have 6 here.
Right, right.
Then you'd write this as 11 minus 5. I just happened to, I usually think of this as A and this is B, and then in my head the formula is A minus B. But it totally doesn't matter. Is everybody with me on that? So there is some variability with this that you can incorporate. So the trick now is to rewrite this equation. So what you're going to do is you're going to put the 5. The 5 is the number that goes with the mod 8. So put the 8 over with the 5, right? So subtract the 8 over, and then move the 11 to the other side, like this, okay? So take this expression here, and you have negative 43, right? This is negative 43 right here, and of course this is the same thing. Okay, that is the answer now. Because modulo 8, negative 43 is the same as 5. Right? And modulo 11, negative 43, I'm sorry, modulo 18, negative 43 is the same as 11. Pretty simple. So just reminding you about that. I wrote out like a general procedure in the notes. If you go back to wherever that was, probably in March, when we explained that.
Yeah, can you explain the last step?
The very last step?
Yeah.
Yeah, so I replaced the negative 6 with 5 minus 11. I look back here,
Yeah.
and I see the 5 and the 8 are together. So I put the 5 and the 8 together on the same side. So I keep this and put this one over there with it, right? On the left side. And then I keep the 11 and the 18 go together. So I put those over on the other side together, right? So this goes with this one. And now, this is an equal sign. This is not a congruence, right? This is literally an equal sign. So you're saying this number equals this number. You figure out what that number is, that's your answer, right?
Yeah, but you said that the right-hand side is in mode 18, the old.
If we take the left side, if we reduce it mod 8, we get 5.
Oh.
And the right side, if we reduce it mod 18, we get 11. Right, that's exactly right. Yes?
So the final answer would be like x congruent to negative 43
That's it.
Okay.
X is congruent to negative 43 modulo 72. Of course, you could add 72 to that and report a different answer. So X is also congruent to, what would that be, 29 mod 72. So 29 also works, positive 29. But there's a unique answer modulo 72 here. Okay? Does everybody remember this? Okay. I did it with general letters, you know, with A and B and N and so on, back in N and M, back in the notes from the class. So if you need to kind of go back over that one more time, by all means, go ahead and do that. So we have a unique solution here, modulo 72.
So one more question. Why
Yeah.
do you say there is only one solution?
Why do we say there's only one unique solution?
Yeah.
So the theory tells us that there is, whenever you have a system of congruences and the mod is not relatively prime to one another, then you get one unique solution modulo the LCM of those primes. By the way, if you have several of these, let's say you also had another one, x is congruent to 1 modulo 26 or something like that, right? What you would want to do would be to take them 2 at a time. Okay, so figure out the first one. This would give you a solution modulo 72. Then you would take the 72 and pair it up with the 26 and play the game again. Right, so you can do this with more than just 2 of them, but then it takes a little bit more patience to get to the answer. Okay. Am I jogging people's memories? You know, one other thing, I did a review session yesterday for my other class, and I'm going to tell you guys the same thing that I told them. You're not going to walk out of here after the review saying, oh, gee, I'm good to go, I'll show up Wednesday, I don't have to think about this anymore. You know, the idea of the review session is more to just put things back in your head again. Oh, yeah, I remember that. Oh, I need to review this again. Or, yeah, that's a good point, I forgot that. Right? Just to kind of get your memory jogged. It doesn't mean that you're going to walk out of here like, oh yeah, I'm ready for the test. Why don't you give it to me now? You know, that's not what we're trying to do here. Okay, let's do another one. Let's do another one. Remember, we're finding all solutions. So part B, x to the 4th plus 5x cubed plus 4x squared minus 4x minus 3 congruent to 0 modulo 52. Is 52 prime? No, okay. Not going to help us. Darn. I'm going to solve this for x. Now, there was an earlier problem where we had a power of x, I think it was x to the 6th, and we took the index of the equation in order to bring the exponent down in front and work with it that way. But that was with a single power of x. There was a coefficient in front of it. It was just a single power of x, I think. This is like a whole entire set of terms added together. So if I just put a big index in front of the left side here, the index does not respect the plus signs in the same way that logarithms don't respect addition, right? So we aren't quite in the same position to be able to use the index on this one like we were the earlier one. Okay, so we're looking for roots of this polynomial. Anybody have any thoughts here? Okay, 52. How do we factor 52? Yeah, 2 squared times 13. Okay? Now, by the way, if we were looking at this congruence modulo 13, 13 is a prime. And at that point, we could remember Lagrange's theorem. Remember, Lagrange's theorem tells you that as long as you're looking at a polynomial modulo a prime, the number of solutions to it is at most the power of the degree of the polynomial. Now, any solution that does work modulo 52, in other words, if 52 divides the expression on the left side, then so does 13, right? So, you know, you could actually say to yourself, you know what, I'd rather start with a simpler problem, and I'd look at it modulo 13. 13 at least is a prime. Now we at least, you know, have Lagrange's theorem. We know there's not going to be more than 4 solutions here, okay? But still, how would we approach that, though? If we were doing it mod 13, what might you do? You're on the test, and time is of the essence, and you've got to figure this thing out. Modulo 13, you don't, let's say you forgot every single theorem you learned all semester long. You don't remember anything. What are you going to do? You only got 13 numbers to plug in, right, at this point. You can plug in 0, that doesn't work. Plug in 1, that won't work. Plug in 2, that won't work, right? And you could just brute force it that way. You know you're only going to get at most 4 answers that do work. Okay? So you could just do that. All right? So that's one way. That's kind of a simple way. Would there be something else that we could do instead of that, though, that's along the same lines?
Same idea as if it has a solution mod 52, then it has that 113 and 2 squared, so we can reduce it to 4.
We could have just as well looked for solutions modulo 4. That's exactly right. Now, let's say we do this for mod 4 and for mod 13. Let's say we get some solutions. Then what am I going to do? I've got x congruent to this, and this mod 4, and x is congruent to this, and this mod 13. What would I then do with all the information I have? The Chinese remainder theorem again, right? So I can build myself back up to mod 52 by first doing mod 13 and mod 4. Isn't that clever? Okay, and actually in mod 4, you only have 4 choices of numbers to plug in. If you put in 0 on the left, let me just call this p of x for a second. So p of 0 is -3. P of 1 is 1 plus 5 plus 4 minus 4 minus 3, which is 3. Okay, P of 2, if I just plug in 2, I'll get what? 16, help me out with the numbers here. 16 plus 40, that's 56, plus another 16, 72, minus 11 more, that would be 61. Okay, and then, by the way, instead of doing P of 3, we could do P of -1. If I'm working modulo 4, I could just as well plug in -1. It's the same thing as +3. So if I put in -1, I get 1 minus 5, that's -4, plus 4, which is 0, and then plus 4 again, and then minus 3, that's 1. In mod 4, are any of those things equal to 0? No. So, guys, this has no solutions mod 4. There are no solutions mod 4. If there's no solutions mod 4, if 4 never divides this expression, then 52, of course, never divides this expression. It says find all solutions, if any, and there are no solutions. So P of x is not congruent to 0 mod 4 for all x. Okay, so thus no solutions mod 52. So guys, I can give you a pretty big mod. You wouldn't want to do 52 different numbers into the equation, right? But if we think about it mod 4 and mod 13, that's not so bad. Okay? You guys with me? Actually, if you're reducing at mod 4, you can just like cross this part off, just write it as x to the 4th plus x cubed plus 1. Right? This is 5 is the same as 1. That's the same as plus 1. You just have to plug 4 numbers into that. Plug in 0, plug in 1, plug in 2, and plug in 3. Or, even better, plug in 0, plug in 1, plug in 2, and plug in -1. That's going to take you less than 30 seconds probably. So at this point, it becomes very simple. Now, if you do find solutions mod 4, then you might need to look at mod 13 as well, because something that's a solution mod 4 is not necessarily a solution mod 52. So,
We don't have a way to solve this other than playing.
brute force. At this point, brute force is really it. Yeah, exactly. There's not really anything else that we learned. If we could somehow express this left side as like a perfect square or something, then maybe we could use a quadratic residue theory. But we mainly work with linear congruences and quadratic congruences, and this is not of low enough degree that we really have any procedure for it. If you remember the proof of Lagrange's theorem, which was talking about finding solutions to these polynomials, it was not constructive. It did not construct solutions for you. It was just an induction proof where you said, well, if it was true for a polynomial of degree 3 that you had these 3 solutions, then here's how you would get 4 solutions to a 4th degree polynomial. It was totally not constructive. There was no procedure there for solving it. The congruences that you want to be able to solve are the linear ones and the quadratic ones when possible. You want to know when it's possible, and you want to be able to do it when it is possible. Right. Yeah, Lucy?
Yeah, how do you choose 0, 1, and 2, negative 1 to build in the polynomial?
Well, if I'm looking mod 4,
Uh-huh.
in mod 4 I only have 4 numbers, right? Those numbers are usually thought of as 0, 1, 2, and 3. But 3, already 3 to the 4th makes my head hurt. So instead of that, I just change it to a negative 1. Yeah, that's the reason I did that. Yeah, okay, yeah, James?
Couldn't you just take it one step easier and do it mod 2?
Yeah, why not? Yeah, mod 2. There's no solutions mod 2. This is always odd, right? It never comes out to 0. So there's no solutions mod 2. I love it. Okay, yeah. All right. Everybody good with that one? Okay, let's do one more. I guess the reason I stuck with mod 4 is just because when you're thinking of using the Chinese remainder theorem, the 2 moduli you're going to have are 4 and 13. Yeah, but your point is well taken. Okay, here's one more. This is still on the same problem, number 5, part C. So again, find the solution if possible. Negative 2x squared plus 5x plus 1 quantity squared is congruent to 0 modulo 29. Okay. Now, this one is also a 4th degree polynomial, just like part B. It's still a 4th degree polynomial, but this one is a little bit more hopeful, I would say, in terms of at least trying to approach it, because you're basically saying here that 29 needs to divide this thing. In other words, it needs to divide the product of this number times itself. So can we simplify that? How so? Once we, what Crystal's suggesting is the sort of the change of variables. Once we get it down to a quadratic equation, we can use a change of variables. It currently is not a quadratic equation. It is a 4th degree equation. So how do we reduce it to a quadratic equation so that we can use Crystal's idea? James?
First solve like just for x squared is congruent to 0 mod 29, and then plug those solutions in for the negative 2x squared plus 5x plus 1.
So you just want to solve this?
Right, and then set so we'll get solutions for that, and then set negative 2x squared
Well,
plus
the
5x
solutions
plus
for
1.
this are going to be 0.
Right, exactly.
Okay, so this is going to be 0.
No, we did with two change of variables, like what w equals like inside, and then w squared equals that, and then
Maybe that's kind of what you're
Basically,
suggesting. Yeah, I mean, it turns out it's not necessary to do that. You can do that, but I just want to remind you guys, this is just saying that 29 divides negative 2x squared plus 5x plus 1 squared, right? What kind of a number is 29?
Prime.
Prime. If I have a prime number that's dividing a product of two things, what can you tell me if P is a prime and it divides a product of two things? It divides one or the other of those, right? P divides A or P divides B, right? Well, in this case, the A and the B are just 2 copies of the same thing, right? So you can basically just get rid of the square on that. Okay, so we don't actually need to really change variables for that. We can literally get away cheap here and just reduce it like that. Okay? All right, so let's go ahead and see if we can just work on this one now. Do you remember the formula for the change of variables? What is it? Y equals 2ax plus b, all right. D equals B squared
minus 4AC.
minus 4AC. That's it. Okay, you want to make sure you guys remember that one, right? And the A, B, and C are right here in this expression. So let's plug in the numbers that we know. The A is negative 2. So we're going to get negative 4x, and the B is 5. So negative 4x plus 5, that equals y. And then for the D equation, we have B squared, which is 25, minus 4AC. We're subtracting negative 8, so I believe that comes out to 33. Okay, let's see if that's what I got. Yeah, and of course we're going to be reducing these things modulo 29. Everything is going to be mod 29 here. Okay? So the first question is, y squared congruent to 33 mod 29? Well, I can reduce that to a 4, right? Is there any solution to this? Definitely. What are the solutions?
Plus or minus 2.
Plus and minus 2. Very good. Okay, so y is equal to plus or minus 2 mod 29. And then from there, we can hopefully go back and figure out what x is. So let me come back to this side. We have 2ax plus b, which is negative 4x plus 5. And we're going to be setting that equal to our y value. So negative 4x plus 5 is going to equal, let's do first of all the case of 2 mod 29, or we also have the other case, negative 4x plus 5 congruent to negative 2 mod 29. Okay? So these won't be too hard to solve, I don't believe. If the first one, if we just subtract the 2 over and put the 4x on the other side, we're going to get 3 is congruent to 4x. And now I can multiply by the inverse of 4 in mod 29. What's that going to be?
Is it negative 7?
It is negative 7, yes. Because 7 times 4 is 28, but I need negative 28 because that's the same as positive 1. So I'm going to get a negative 7. I'm going to multiply by a negative 7 here, and that's going to give me x. In other words, that's the same as positive 8. So x is congruent to 8. That's one solution. If I go on the other side, I can add the 2 to the left side and put the 4x on the other side. Again, I can multiply by negative 7. So that's going to be negative 49 is congruent to x mod 29. And I'm going to add 58 to that, I think, because 58 is the same as 0. I'm going to get 9. So x is congruent to 9 mod 29. So these are actually 2 solutions here. What's the most number of solutions that this congruence could even have? Only 2. We found 2, so we're done. Okay? And those same 2 solutions solve this congruence.
Did you say that last part again?
So this is a quadratic congruence. So it can have, right, it can have at most 2 solutions modulo a prime. Of course, 29 is prime. So you can have at most 2 solutions, and that is how many I found here. That is how many I have. 2 solutions. I cannot have more than that. So I must have them all. And the original congruence was a 4th degree polynomial. So the theorem, Lagrange's theorem, says that, well, a modulo a prime, a polynomial of any given degree will have at most that many solutions. So at most 4 solutions. It turns out this one only has 2. Does that make some sense?
When we talk about, well, multiplicity, that's essentially where the ones come up, right?
Yeah, that's right. You could say that the 8 and the 9 are both like a double root. Exactly. That's a good point. What would you do? I didn't prepare this as an example, but what would you do if this modulus was not a prime here? What if this was like mod 58? Factor, just like the last example, right? With the previous one, you'd say, well, 58 is the same as 2 times 29. You'd solve it mod 29. You'd solve it mod 2, okay? and then you would use the Chinese remainder theorem to paste together the solutions. Okay. So guys, when you're looking at the modulus, if it's already a prime, that's great. If it's not, then try to think about factoring it into primes. That's very often the best thing to do. Now, there are some exceptions to that, but that's a pretty good general rule. Okay. Just trying to figure out what else I want to do here. Okay, let's do this one, number 6. Oh, I wasn't going to use that board. Let me come back over here again. Can I erase over here? Okay. So let's do a more recent problem. Okay, so here's a more recent one, number 6. If possible, express each integer as a sum of 2 squares. Okay? So I'm going to give you sort of 3 parts on this. The first one is 500. Can you guys remind me, how do we approach this?
You factor it and then put it into groups on n and m.
So 500 is 2 squared times 5 cubed, as it turns out. It's 100 times 5, and then, so you get one extra factor of 5 there. 2 squared times 5 squared, and then extra 1. So what you want to do, can you repeat that for me, Ray, now that I...
Yeah, sorry. So you're going to pick values to put into an n and an m. So it would be 2 times 5, and that's all raised to a 2, and then we have 5 left over.
Okay, great. So you try to put everything that's into a perfect square together. This is the format in the results we did in class. We wrote that as capital N squared times the little m. The little m here is always square free. So you take out anything that would have made a perfect square, you shove that into the capital N part, right? So there you go. Okay, and then what you want to do, if you remember, is look at the square free part. This is the key, right? As long as there are no primes of the 4k plus 3 form over here in the m part, then it is possible to do this, okay? So essentially what you're going to do here, 2 times 5 squared, you're going to take 5 by itself, which is not of the 4k plus 3 form, right? It's of the 4k plus 1 form. You're going to write that as a sum of 2 squares. So that's going to be 2 squared plus 1 squared, right? And then what you're going to do is distribute the 10 squared into that. So basically the 2 gets multiplied by 10, and the 1 gets multiplied by 10. So you get 20 squared plus 10 squared. There's your representation, 400 plus 100. So everybody see what I did? This is, if you prefer, you can just think of this as 10 squared times 2 squared plus 1 squared. And you're just putting the 10 inside of both of those positions. Okay? All right, let's take another example. This is pretty recent, so I'm thinking it might be pretty familiar, but I figure I better say something about it or you won't think it's important. Okay, so here's part B, 6,789. Would you like me to factor that for you? You know, don't forget my little factorization tips. You know, a number is divisible by 2 if it ends in an even number. Right?
I think this was divisible by 3 because all the digits added to a multiple of 3.
Right, if you add up the digits and you get something that's a multiple of 3, then your number is divisible by 3. Of course, you can do this with a calculator also. Just divide by 3 and see if there's any decimal part of the answer. But it's just nice to know these facts.